my great pleasure to make this presentation today. I'm Jiao Su, a master student from National Sanyashan University in Taiwan. The title of my study is Peptide Sequence Design for the Highest Binding Affinity with Different Platinum Facets using the molecular simulation. This is outline of my presentation. First, I will introduce my background and the motivation for my work, and I will show the simulation method and the model in this part. Then I will discuss my result in detail. Finally, make some conclusion for my work. Nowadays, nanoparticle can be proven as a potential catalyst with excellent performance in various reactions. For example, oxidation, isomerization, and isomerization. Can the effect efficiency between the nanoparticle is heavily depend on their size and shape. The previous study in 2011, Huang's group proposed the new process to synthesize the specific shape of platinum nanoparticle. They show the S7 is the excellent capping engine during the platinum nanoparticle synthesis to process the for enhancing the PD11 facet growth. But the detailed mechanism between the capping engine and the nanoparticle is not clear and difficult to investigate in experiments directly. There are some studies propose the different absorption affinity between the peptide and the PT facet may be the key issues of this technique. So, in this study, we use the systematic search method, which called stochastic tunneling basin hopping method, to find the most stable absorption structure of peptide and peptide on the PT facet. And we analyze which amino acid may be the specific key role to PD11 and the PD100 facet. Finally, the reason we designed a set of S7 variant peptide is to compare the effector of different position of amino acid with the original S7. The structural model of S7 peptide is shown in Figure A, and the two facets are shown in Figure B. In the right side, I will introduce a set of S7 variant peptides, which can be shown in three parts. The first part is sequencing of original S7, and the second part is sequencing of connection of PHE and the PRO. And the last part is the separation of PHE and the PRO. The study includes two force fields. The multiplied amber force field is used to describe the interaction of peptide, which has proven as well described for the amino acid. And the interaction between the peptide and the PT facet is used Chalmers force field, which has been modified and applied to the previous absorption studies on the metal successfully. And the PT facet is fixed during the whole separation process. The initial model of the S7 peptide and the PT facet are constructed by Tinker and the Material Studio software respectively. Next, the topology information and the corresponding amber force field parameter of those molecules are converted into LAMS format. In order to find the structure with high binding affinity between the PT facet and the peptide, the basin hopping method is applied to search the most stable absorption structure between them. The principle of basin hopping is changing the distance and the orientation between the peptide and the PT facet randomly. Next, the random structure is minimized by molecule statics calculation and approach to the local minimum structure. Finally, after obtaining source of local minimum structure, the most stable absorption structure may be approached. And the molecular dynamic simulation is applied to the structure which which has been obtained by previous spacing orbit. First, we and optimized by the conjugate gradient method, and we place the amount of water molecules and optimize sequence. The MD simulation was carried out in NBT assemble at 20 room temperature. The time step set as 0.5 nanosecond and performing during 3 nanoseconds. Finally, we analyze the equilibrium structure in vacuum and in water systems. There are whole diagrams of my simulation process. We can see the peptide absorbed upon the PT facet after basing organ, and the place amount of water molecule around the peptide, finally relaxing by the molecular dynamic simulation. The latter profile shows the binding energy of respective amino acid of S7 with the PT111 and the PT100 facet in vacuum, and the right profile is in the water. We can see the two red circle. The binding energy of each amino acid didn't have significant change in the vacuum and in water. Now we can see the change of pHEs clearly in this figure. The red circle represents the aromatic ring, which is part of pHE. Is still stable and the flake on the PT111 after relaxing in water. But the aromatic ring is stand up after relaxing in water, so we may propose that the pHE is the key specific amino acids to distinguish the two facets. The left figure shows the pHE are absorbed on the PT111, and the 3 layers of PTs are represented in color white, red, and yellow. We can see the pHE has strong absorption due to which aromatic rings has good matching with the 3 layers of PT111. So we may propose that the local line key structure may be the reason for promote the PT111 facet growth. And the right figure show the PRO amino acid also have the significance, but also show the phenomenon of the local line key structure. But not all of the pHE in the S7 will be phased up. We find if PRO have no luck, the pHE will stand up in the water, and if PRO luck, and pHE will raise up. So we suppose that PRO also play a big role about the absorption on the PT111. So we have decided to 5 sets of connection of pHE and the PRO, and the 2 sets of separation of pHE and the PRO. The pHE of variant 2, 3, 4, 6 is raised on and lock, and the variant 5 is raised on but no lock. And the variant 0 and 1 is stand up after relaxing water. So we suppose that the position of pHE cannot to be close to the N terminal. We can prove it by variant 0 and 1, and no, we can prove it by variant 0 to 4. And according to variant 5 and 6, we can see the amino GLN is the high molecular weight polarity amino acid, and the SER is much lower compared with GLN. So, which means the pHE of variant 5 is become unstable is because the GLN and the pHE will fight against for the absorption site each other. This is my summation conclusion. The orientation between the aromatic ring of pHe of A7 can form the local-like key structure geometry. And this is the main reason why the pHe is a specific amino acid to compare to PT111 and the PT100. Next, the original S7 case. If PRO have no lock, pHe will be stand up after relaxing in the water environment. In connection of pHe and the PRO case, the position of pHe cannot to be close to N terminal. In the separation of pHe and the PRO case, we can find out that position near the two sides of pHe cannot connection high molecular weight polarity amino acid. Otherwise, this will cause the pHe become unstable and no lock. Finally, we thank National Science University and the Ministry of Science and Technology of Taiwan. The photo show our members. Thank you very much for your attention.
Thank you, Ms. Su, for a very nice talk. Okay, so now do you have any questions? Okay, so I might have some questions for you. So why do you want to study the interaction between the platinum and the peptides? What is this purpose for? Why do you want to study for the interaction between the platinum and the peptide? What is the purpose for? What is your project for? Yeah.
Because the nanoparticle can try to